The morning of November 15th, 1944, at the Kummersdorf proving ground outside Berlin, Oberst Wilhelm Steinberg watched his test crew load a captured American rocket launcher onto the firing stand. The olive drab tube looked crude compared to German engineering welded steel, simple iron sights, and a wooden shoulder stock that belonged on a hunting rifle, not a precision weapon. Steinberg had spent 3 years perfecting the Panzerfaust, Germany's answer to Soviet armor. The latest model, the Panzerfaust 100, could penetrate 6 inches of homogeneous steel under optimal conditions. That figure had been achieved through careful metallurgy, shaped charge optimization, and months of testing against captured enemy tank sections, 6 inches. It was a number the Wehrmacht had learned to count on. But scattered reports from the Western Front suggested the American weapon, this bazooka, as captured documents called it, was achieving something unprecedented. Field commanders claimed penetrations of 8 inches, sometimes more. Steinberg was here to determine if these reports represented battlefield exaggeration or a fundamental gap in German anti-tank technology. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The weapon lying before him embodied everything German military engineers found distasteful about American design philosophy. Where the Panzerfaust featured precisely machined components and carefully calculated explosive charges, the bazooka appeared almost agricultural in its simplicity. The launch tube was nothing more than electrical conduit. The sights were basic iron posts welded to the barrel. The firing mechanism used doorbell wire and a flashlight battery. Yet this crude device had been terrorizing German armor from Normandy to the Rhine. Panzer crews reported devastating hits that punched through frontal armor plates the Panzerfaust couldn't touch. The psychological impact was becoming measurable. Tank commanders were refusing to advance without infantry support, slowing offensive operations and disrupting tactical coordination. German anti-tank doctrine in late 1944 remained rooted in precision engineering and careful deployment. The Panzerfaust program had begun in 1942 as a direct response to Soviet 34 tanks that were devastating German infantry. Dr. Heinrich Langweiler's team at the Hassag Ammunition Works in Leipzig had developed a shaped charge warhead using RDX explosive, mounted on a simple wooden launching rod. The system worked through elegant simplicity. A black powder charge fired the warhead forward while simultaneously launching the empty tube backward, cancelling recoil forces. The shaped charge could penetrate armor by focusing explosive energy into a narrow jet of superheated metal, burning through steel like a blowtorch through butter. By 1944, German factories were producing over 700,000 Panzerfausts monthly. The weapon had proven devastatingly effective against Soviet armor, capable of stopping 34 tanks from ranges up to 100 meters. More importantly, the Panzerfaust required minimal training. A teenage Volkssturm recruit could master its operation in 30 minutes. But the Panzerfaust had limitations that German engineers understood but couldn't easily solve. The weapon was single-use, becoming dead weight after firing. The wooden launching tube and simple black powder propellant meant limited accuracy beyond 60 meters. Most critically, the shaped charge warhead, despite using high-grade RDX explosive, could only achieve 6 inches of penetration against homogeneous steel. American armor doctrine presented challenges the Panzerfaust wasn't designed to handle. The Sherman tank's frontal armor measured only 3 inches thick, well within Panzerfaust capability. But American tank destroyers like the M10 Wolverine featured 5 inches of frontal plate, and the new M26 Pershing heavy tank mounted 4 inches of face-hardened armor that effectively performed like 6 inches of standard steel. More troubling were the reports about the American bazooka's performance against the Tiger tanks. The Tiger I's frontal armor measured 4 inches of quality steel, angled at perfect perpendicular. Panzerfaust hits at close range could penetrate, but required precise targeting and optimal impact angles. American bazooka teams were reportedly punching through Tiger armor from oblique angles that should have caused deflection. Intelligence reports from the Ardennes offensive in December 1944 described American infantry teams destroying Tiger tanks with single bazooka hits to areas German engineers considered immune. The 5th Panzer Army's after-action reports mentioned multiple instances of frontal penetrations against vehicles that Panzerfausts had previously failed to stop. These reports forced uncomfortable questions about German-shaped charge technology. The Wehrmacht's technical superiority had been an article of faith since 1939. German optics, metallurgy, and precision engineering were acknowledged worldwide. The idea that American mass production might have produced a more effective anti-tank weapon challenged fundamental assumptions about industrial warfare. Dr. Langweiler had been requesting captured American bazookas for analysis since September 1944, but procurement proved difficult. The weapons were priority intelligence targets for multiple German research facilities. The few bazookas recovered from battlefields usually arrived damaged by combat or deliberate sabotage by retreating American forces. The specimen at Kummersdorf represented months of effort by German intelligence networks. A complete M9A, one bazooka launcher, with 12 intact rockets, captured during the failed Operation Market Garden in September. The weapon had been shipped directly to the proving ground without field testing, its explosive potential intact. Steinberg's test protocol followed standard German procedures developed for evaluating captured enemy equipment. Static firing trials against calibrated armor plate, followed by ballistic analysis of warhead performance and chemical examination of explosive components. The target array consisted of steel plates from destroyed German vehicles, sections of Panzer IV hull armor, Tiger Eye turret plate, and captured American Sherman components for comparison. The first rocket loaded into the bazooka's breech was a standard M6A3 warhead, manufactured in 1944 at the Oldsmobile facility in Lansing, Michigan. German intelligence had identified the production codes stamped on the warhead casing, but couldn't decipher the explosive composition without destructive testing. At precisely 10:30 a.m., Steinberg gave the firing command. The rocket whooshed from the tube, trailing white phosphorus smoke, crossed the 100-meter range in less than 2 seconds, and struck the Tiger Eye armor plate with a sharp metallic crack that echoed across the proving ground. What happened next stopped every man at the firing line. The shaped charge jet hadn't just penetrated the 4-inch plate, it had burned completely through and carved a crater in the concrete backstop 3 feet behind the target. The entry hole measured exactly 3 1/8 inches in diameter, clean and precise as a machine-drilled opening. Steinberg walked to the target frame and examined the penetration. The warhead had punched through steel that required direct hits from 75mm anti-tank guns to defeat. A man-portable weapon had achieved what German industry considered the performance ceiling for shaped charge technology. The second shot targeted a section of Panzer IV frontal armor, 3 inches of homogeneous, steel angled at 20 degrees from vertical. The rocket struck just left of center and penetrated effortlessly, creating massive spalling on the rear surface that would have killed every crew member inside the fighting compartment. Shot 3 was aimed at a piece of American Sherman armor, 3-inch plate from a tank destroyed in France. The bazooka warhead went through like the armor wasn't there, confirming that American weapons could defeat American armor with devastating effectiveness. By the 4th shot, Steinberg realized he was witnessing something that German weapons science had declared impossible. The American rockets were consistently achieving 8 inches of effective penetration, measured as the maximum thickness of armor they could defeat. This wasn't battlefield exaggeration or propaganda. It was measurable, repeatable performance that exceeded German capabilities by 33%. The test crew examined each warhead fragment with forensic precision. The explosive charges were significantly larger than comparable German warheads, but size alone couldn't explain the performance difference. The shaped charge liners appeared to be copper, similar to German practice, but manufactured to tighter tolerances than German wartime production could achieve. Most unsettling was the explosive itself. Chemical analysis of residue samples suggested an RDX-based composition similar to German formulations, but with additional metallic components that enhanced the shaped charge effect. The Americans had apparently solved metallurgical problems that German chemists were still struggling with in late 1944. Dr. Langweiler arrived at Kummersdorf that afternoon to examine the test results personally. His reaction was recorded in the facility's logbook. The American weapon achieves performance parameters we considered theoretical maximums. Our current production methods cannot duplicate these results. Coming from Germany's leading shaped charge expert, this admission represented more than technical analysis. It was an acknowledgement that American industrial chemistry had surpassed German capabilities in a field where Germany had led the world since 1939. The psychological impact on German engineers was immediate and profound. They had spent 5 years perfecting weapons based on the assumption that German technical superiority would overcome Allied material advantages. The Bazooka tests suggested that assumption was fundamentally wrong. American industry hadn't just produced more weapons, it had produced better weapons. The crude-looking tube launcher housed sophisticated metallurgy and explosive chemistry that German laboratories couldn't match. Mass production hadn't compromised quality. It had enabled precision that German craftsmanship couldn't achieve under wartime conditions. The November 15th test report reached Berlin within 48 hours, marked with the highest classification levels. Copies went to the Reich Ministry of Armaments, the Wehrmacht's Technical Bureau, and Heinrich Himmler's SS research facilities. The conclusions were stark. American anti-tank weapons had achieved decisive technological superiority that German industry couldn't match with available resources. For an army that had built its reputation on technical excellence, this represented a crisis that went beyond military capabilities. The Wehrmacht's entire self-image was based on superior German engineering, defeating Allied quantity through quality. The Bazooka tests proved that premise false. The captured weapon had demonstrated that sometimes the side with better chemistry wins, regardless of whose engineering traditions run deeper or whose manufacturing processes are more elegant. In the sterile environment of a German proving ground, American industrial science had delivered a verdict that no amount of Germanic precision could overturn. Part 2. The secret behind the American bazooka's devastating performance lay not in revolutionary design, but in chemistry that German scientists had explicitly rejected as too dangerous for mass production. While German engineers pursued precision and safety in their Panzerfaust program, American weapons developers had embraced explosive compounds that European laboratories considered unmanufacturable at industrial scale. The story begins in 1942 at Harvard University, where a 38-year-old Lithuanian-born chemist named George Kistiakowski was violating every safety protocol his academic colleagues considered sacred. Working under a classified contract from the National Defense Research Committee, Kistiakowski was synthesizing compounds that had killed dozens of workers in British and German facilities. His target was something chemists called composition B+, 60% RDX, 35% TNT, and 5% aluminum powder. The aluminum was the key innovation, and it was also what made the mixture so lethally unstable during production. When aluminum particles mixed with RDX under pressure, they created what ammunition specialists called a sympathetic detonation risk, meaning one spark could chain react through an entire factory. British weapons researchers had attempted aluminum-enhanced explosives in 1941, but abandoned the program after a catastrophic explosion at the Woolwich Arsenal killed 23 workers and injured 67 more. The blast crater measured 40 feet across and was visible from reconnaissance aircraft. His Majesty's Explosive Research Establishment classified aluminum-loaded RDX as unsuitable for mass production under any circumstances. German chemists reached similar conclusions through more cautious experimentation. Dr. Rudolf Schmucker's team at the Dynamit Nobel facility in Troisdorf tested aluminum-enhanced charges in 1943, but limited production to small laboratory batches after 3 separate detonations destroyed equipment and injured personnel. German safety regulations, ironically more stringent than American standards, prohibited large-scale manufacture of aluminum-loaded explosives. Kistiakowski approached the problem with academic arrogance that proved strategically decisive. He believed German and British failures resulted from inadequate process control, not fundamental chemical impossibility. Working with DuPont engineers at the Holston Army Ammunition Plant in Tennessee, he developed production methods that German industrial chemists had never attempted. The breakthrough involved temperature control precise to within 2 degrees Celsius and humidity regulation that prevented moisture from triggering premature reactions. Workers wore grounded copper clothing and operated machinery designed to eliminate static electricity completely. The entire production line was surrounded by blast barriers and monitored by sensors that could detect gas emissions indicating thermal runaway. Most importantly, Kistiakowsky insisted on continuous production rather than batch processing. German and British facilities had attempted to mix aluminum and RDX in large containers, creating concentrated explosive masses that detonated catastrophically when problems occurred. The American system mixed small quantities continuously, flowing through sealed pipes that limited potential blast effects. By September 1943, the Holston plant was producing 12 tons daily of composition B+, without major incidents. This represented more aluminum-enhanced explosive than German and British laboratories had manufactured during their entire research programs combined. American industrial chemistry had solved a problem that European experts considered unsolvable. The performance difference was immediately measurable. Standard composition B warheads achieved 6 inches of armor penetration under optimal conditions. Composition B+ consistently reached 8 inches, with occasional tests exceeding 9 inches depending on target material and impact angle. The 5% aluminum additive increased shaped charge effectiveness by approximately 33%. The metallurgical explanation involved physics that German weapons scientists understood but couldn't replicate safely. When aluminum particles vaporized during detonation, they enhanced the temperature and velocity of the shaped charge jet, allowing it to burn through steel more efficiently. The aluminum also created a secondary combustion effect that continued destroying armor after the initial penetration, causing massive internal damage that killed tank crews even when the main jet didn't completely penetrate. German intelligence agencies were aware that American bazookas used enhanced explosive compositions, but they couldn't determine the specific formulation or production methods. Captured warheads provided chemical residue for analysis, but the explosive had already detonated, destroying the precise molecular structure that gave it superior performance. Dr. Langweiler's team at Hassag attempted reverse engineering based on residue analysis from the Kummersdorf tests. They identified aluminum particles and RDX components, but determining the exact proportions and production techniques required months of dangerous experimentation that German facilities weren't equipped to conduct safely. The first German attempt to replicate composition B+ resulted in a factory explosion at the Werktanne facility near Clausthal-Zellerfeld in February 1945. 17 workers died, and production equipment worth 2 million Reichsmarks was destroyed. The blast was so powerful that Allied reconnaissance flights photographed the crater, prompting intelligence analysts to wonder if Germany was testing new weapons. A second attempt at the Dynamit Nobel plant in March 1945 killed 11 more workers and convinced German authorities that aluminum-enhanced explosives were beyond their manufacturing capabilities. The Reich Ministry of Armaments classified the program as strategically impractical and ordered all research discontinued. By then, American factories were producing over 50,000 aluminum-enhanced bazooka warheads daily. The Oldsmobile plant in Lansing had been joined by General Motors facilities in Flint and Grand Rapids, creating combined production capacity that exceeded total German Panzerfaust output while achieving superior performance per round. The industrial scale was staggering. American ammunition plants consumed more aluminum monthly for bazooka warheads than Germany's entire aircraft industry used for fighter plane production. The United States had effectively weaponized its aluminum surplus, turning industrial capacity into battlefield superiority that German precision engineering couldn't match. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The tactical implications became apparent on European battlefields throughout 1944 and 1945. German tank crews reported that American Bazooka teams could engage from longer ranges and achieve penetrations that Panzerfausts couldn't duplicate. The psychological effect was measurable. Panzer units began refusing to advance without extensive infantry support, slowing German offensive operations. American infantry discovered they could destroy German tanks that were theoretically immune to their weapons. The Tiger I, with 4 inches of frontal armor, had been considered bazooka-proof based on earlier combat experience. But composition B+ warheads were punching through Tiger armor consistently, forcing German tank commanders to completely revise their tactical assumptions about American infantry capabilities. The Panther tank presented an even more dramatic example. Its 5-inch frontal plate, angled at 55 degrees, from vertical, provided effective protection equivalent to 8 inches of perpendicular armor. German engineers had designed the Panther specifically to defeat Allied anti-tank weapons, including early bazooka models. But American troops in late 1944 were achieving frontal penetrations that German ballistics calculations had declared impossible. Combat reports from the Battle of the Bulge in December 1944 documented multiple instances of bazooka teams destroying Panthers from direct frontal engagement. The 101st Airborne Division alone reported 11 confirmed Panther kills using bazookas during the siege of Bastogne, many involving shots that penetrated the thickest armor sections. These results forced German armor doctrine to evolve rapidly. Tank commanders who had operated with confidence based on armor thickness calculations now faced weapons that exceeded those calculations by significant margins. The psychological pressure was enormous. Crews couldn't trust their protection systems against weapons that American infantry carried as standard equipment. German attempts to counter the enhanced American bazookas focused on armor modifications rather than improved weapons. The Wehrmacht began welding additional steel plates onto existing tanks, creating improvised composite armor that added weight but provided uncertain protection. These modifications reduced mechanical reliability and limited operational range, but desperate tank crews preferred slower vehicles to destroyed ones. The Panzer IV received the most extensive modifications, with many units adding 30mm steel plates to frontal and side armor. The additional weight strained transmissions and reduced top speed by 15%, but it provided psychological reassurance to crews who had lost confidence in their original protection. More sophisticated solutions included the development of spaced armor systems, where steel plates were mounted several inches away from main hull armor. The theory suggested that shaped charges would detonate against the outer plate, disrupting the jet formation before it reached critical areas. Testing proved the concept worked against standard charges, but composition B+ warheads often burned through both layers. German industry also attempted to develop improved Panzerfaust warheads using lessons learned from captured American weapons. The Panzerfaust 150, introduced in limited numbers during early 1945, featured larger warheads and enhanced shaped charge liners that increased penetration to approximately 7 inches under optimal conditions. But 7 inches still fell short of the 8+ inches that American bazookas were achieving consistently. More critically, German factories couldn't produce enhanced warheads in sufficient quantities to matter strategically. The aluminum shortages that prevented composition B+ production also limited improvements to shaped charge liners and other components. The fundamental problem was industrial capacity operating under completely different constraints. American factories had unlimited access to raw materials, abundant electrical power, and workers who weren't being bombed nightly by enemy air forces. German ammunition plants operated under resource rationing, power interruptions, and constant air raid disruptions that made precision chemistry impossible. By spring 1945, German weapons development had effectively conceded the anti-tank technology competition. New programs focused on quantity rather than quality, simplified weapons that could be manufactured quickly using available materials. The Panzerfaust Klein, introduced in April 1945, was essentially a disposable-shaped charge launcher that used black powder propellant and achieved only 4 inches of penetration. The strategic implications extended beyond individual weapons performance. American industrial, Chemistry had demonstrated that mass production could achieve technological superiority over traditional craftsmanship when supported by sufficient resources and scientific infrastructure. The Bazooka program proved that quantity and quality weren't mutually exclusive when proper industrial methods were applied. German military leadership recognized this reality by late 1944, but lacked the capability to respond effectively. The Reich's scientific establishment was fragmented among competing agencies, its industrial base was under constant air attack, and critical raw materials were becoming increasingly scarce. Even if German chemists had solved the composition B+ production challenge, the infrastructure to manufacture it at scale no longer existed. The captured Bazooka at Kummersdorf had revealed more than superior American weaponry. It had exposed the complete failure of German assumptions about industrial warfare. The Wehrmacht had believed that superior engineering and tactical excellence could overcome Allied material advantages. The aluminum-enhanced warheads proved that belief catastrophically wrong. In the sterile environment of a German proving ground, American chemistry had delivered a verdict that no amount of tactical brilliance could overturn. The crude-looking tube launcher represented the triumph of industrial science over traditional military engineering, a lesson that would reshape weapons development for decades to come. Part 3 would examine the desperate final German attempts to bridge this technology gap and the lasting impact of American chemical innovations on post-war military development. The Bazooka's legacy would extend far beyond World War II, establishing principles of industrial weapons development that continue to influence military technology today. The final German response to the Bazooka crisis came not from weapons laboratories, but from a 19-year-old Waffen-SS volunteer named Klaus Brenner, who had never seen a chemistry textbook in his life. On March 23, 1945, outside the town of Oppenheim on the Rhine, Brenner achieved something that German industrial science had declared impossible. He stopped an American Sherman tank using a weapon he had improvised from captured materials in less than 30 minutes. Brenner's innovation was born from desperation rather than engineering expertise. His unit, the remnants of the 17th SS Panzer Grenadier Division, had been issued exactly 4 Panzerfaust rounds to stop an entire American armored column. Standard tactical doctrine called for close-range ambush positions, but American infantry had learned to sweep suspected hiding spots with bazooka fire before their tanks advanced. The mathematical problem was stark. 4 rounds against 12 Shermans, with American infantry providing suppressive fire that made traditional anti-tank tactics suicidal. Brenner's solution violated every principle German weapons manuals had established for shaped charge employment, but it worked with devastating effectiveness. He had recovered the warhead from an unexploded American bazooka round, carefully extracted the composition B+ explosive charge, and packed it into a captured American steel helmet along with metal fragments from destroyed German equipment. The improvised device wasn't technically a shaped charge anymore, it was closer to a directional fragmentation mine, but when detonated against the Sherman's side armor, it created penetration effects that standard Panzerfausts couldn't achieve. The tank's crew died instantly. More importantly for German tactical analysis, the improvised weapon had used American explosive chemistry to defeat American armor protection. A teenage soldier with no formal training had accomplished what Germany's most sophisticated weapons laboratories couldn't replicate in factory conditions. Brenner's after-action report, filed with his regimental headquarters, before the unit was overrun 48 hours later, provided the final piece of evidence that German weapons science needed to understand the scope of their technological failure. The Americans hadn't just developed superior anti-tank weapons, they had created explosive chemistry so robust that enemy soldiers could weaponize it using improvised methods. This revelation reached Berlin during the final weeks of the war, but by then, German industrial capacity had collapsed beyond any possibility of response. The Kummersdorf proving ground, where Oberst Steinberg had conducted his bazooka tests, was evacuated on April 15, 1945, with research files scattered or destroyed to prevent capture by advancing Soviet forces. Dr. Langweiler's Hassag facility had been bombed into rubble by Allied airstrikes in February, taking with it Germany's most advanced shaped charge research capability. The dynamite Nobel plant, where German chemists had attempted to replicate composition B+, was captured by American forces on April 8, its equipment intact, but its scientific personnel already fled westward. The Americans who occupied these facilities discovered research that confirmed their weapons had achieved technological superiority that German industry couldn't match. Captured German test reports documented penetration trials showing American bazookas consistently outperforming the best German anti-tank weapons by margins that German engineers had considered impossible. More revealing were the industrial assessments German scientists had prepared for their military leadership. These documents, classified at the highest levels, admitted that American ammunition factories were operating with precision chemistry that German facilities couldn't duplicate even under peacetime conditions. The United States had essentially industrialized laboratory-grade explosive science on a scale that European manufacturers had never attempted. The immediate post-war period brought uncomfortable revelations for Allied weapons specialists who examined captured German research. German theoretical understanding of shaped charge physics was actually superior to American knowledge in several key areas. German metallurgical analysis was more sophisticated, and German ballistics calculations were more precise. But German industrial chemistry operated under constraints that made theoretical knowledge irrelevant. Resource shortages, bombing disruptions, and safety regulations had prevented German factories from implementing production methods that American plants used routinely. Superior scientific understanding meant nothing when it couldn't be translated into manufactured weapons. American technical intelligence teams interviewing captured German weapons specialists discovered a recurring theme. German engineers had identified solutions to shaped charge optimization problems months or years before American researchers, but lacked the industrial infrastructure to implement these improvements at scale. Dr. Langweiler, interrogated by American weapons experts in June 1945, provided detailed explanations of aluminum-enhanced explosive formulations that German laboratories had developed parallel to American research. His team had actually achieved slightly better performance than composition B+ in small-scale tests, but couldn't scale production beyond laboratory quantities without triggering catastrophic factory explosions. The safety differential was stark. American ammunition plants had experienced fewer than 12 fatal accidents during the entire war, while producing millions of aluminum-enhanced warheads. German facilities had killed more than 50 workers in failed attempts to manufacture thousands. American industrial safety systems had enabled mass production of explosives that German methods couldn't handle safely. This industrial capability gap would reshape post-war military development in ways that extended far beyond anti-tank weapons. NATO standardization agreements established in the 1950s required member nations to achieve ammunition production standards that only American-style industrial chemistry could meet. European manufacturers had to completely rebuild their explosive production capabilities using American methods and American safety protocols. The psychological impact on German military thinking proved equally profound. Wehrmacht veterans who transitioned to the West German Bundeswehr brought with them vivid memories of technological inferiority that shaped Cold War defense planning. German military doctrine emphasized NATO integration and American weapons procurement rather than indigenous development programs. When West Germany began developing modern anti-tank weapons in the 1960s, the design requirements explicitly referenced American bazooka performance as the minimum acceptable standard. The Milan anti-tank missile system, jointly developed by France and Germany, was specifically designed to exceed the 8-inch penetration that had shocked German observers in 1944. Soviet military development followed a different but parallel path. Red Army technical intelligence had captured extensive German research on American bazooka capabilities, including detailed test reports from Kummersdorf. Soviet weapons designers used this information to develop the RPG series of rocket-propelled grenades, explicitly designed to match or exceed American performance standards. The RPG-7, which entered Soviet service in 1961, achieved penetration performance comparable to World War II American bazookas while adding improvements German engineers had theorized but never implemented. Soviet industrial chemistry had successfully duplicated American explosive formulations using captured German research as a technical foundation. The bazooka's influence on American weapons development proved equally lasting. The success of Composition B+ led to even more sophisticated explosive formulations that dominated anti-tank weapon design through the Cold War period. The M72 light anti-tank weapon, standard American infantry equipment from 1963 through the present day, uses explosive chemistry directly descended from Kistiakowsky's aluminum-enhanced formulations. Modern-shaped charge weapons like the FGM-148 Javelin missile achieve penetration capabilities that would have seemed impossible to World War II weapons designers, but they operate on the same fundamental principles that shocked German observers at Kummersdorf. Industrial chemistry has continued advancing, but the basic approach, aluminum-enhanced explosives manufactured under precise environmental controls, remains essentially unchanged. The strategic lesson proved equally enduring. Military capability in industrial warfare depends not just on scientific knowledge or engineering expertise, but on the industrial infrastructure necessary to translate laboratory discoveries into mass-produced weapons. Theoretical superiority means nothing without manufacturing capacity that can operate safely at scale. German weapons science in World War II was arguably more sophisticated than American research in several key areas, but German industrial methods couldn't implement advanced chemistry under wartime conditions. American factories achieved technological superiority through industrial engineering rather than scientific breakthrough, proving that manufacturing capability could be as decisive as research innovation. This principle would influence Cold War military planning for both superpowers. The United States emphasized industrial base expansion and manufacturing technology development as strategic priorities equal to research and development spending. The Soviet Union built massive industrial complexes specifically designed to mass-produce advanced weapons using chemistry that required precise, environmental controls. The captured bazooka that had stunned German observers in November 1944 represented more than superior American weaponry. It embodied a completely different approach to translating scientific knowledge into military capability. The crude-looking tube launcher had demonstrated that industrial chemistry, properly implemented, could achieve tactical effects that traditional weapons engineering couldn't match. Klaus Brenner's improvised anti-tank device had provided the final confirmation that American explosive chemistry was so robust it could be weaponized by soldiers with no technical training. In the chaos of Germany's final collapse, a teenager with a captured helmet had achieved penetration effects that German industrial science couldn't replicate in sophisticated laboratory conditions. The broader implications extended beyond military technology to fundamental questions about industrial warfare itself. The bazooka crisis had revealed that scientific knowledge without manufacturing capability was strategically worthless, while industrial chemistry properly implemented could overcome tactical disadvantages that seemed insurmountable. For German military leadership, reflecting on their defeat, the captured American weapons represented a harsh lesson about the realities of 20th century warfare. Superior tactics, better training, and more experienced soldiers meant nothing when the enemy possessed industrial capabilities that could mass-produce weapons your own factories couldn't duplicate safely. The aluminum-enhanced explosives that had shocked German test officers would continue advancing through decades of Cold War development, eventually enabling precision-guided munitions and advanced anti-armor systems that made World War II tank battles seem primitive by comparison. But the fundamental principle established at Kummersdorf remained unchanged. In industrial warfare, the side with better chemistry often wins, regardless of whose military traditions run deeper or whose individual weapons are more elegantly designed. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.